Today is all about the exponential function, ladies and gentlemen. So as we take a look, we got chapter 5.3. We're going to do 2 days on this one. We're going to evaluate and graph these guys. I'm going to show you how to do it by hand, and then I'm also going to show you how to do it by calculator. Okay, when you're doing my math lab, really most of the times you can just use your calculator. Now, if this wasn't Corona time, we'd have to do this by hand. So I'm going to show you both, and then from there you can kind of choose on what you want to do. So again, graphing these things by hand, you use transformations, and then to graph on a calculator, just plug and chug, and should be pretty easy. Again, I'm going to embarrass myself at the end defining the number E using a little song. And then goal number 3, we're going to tackle tomorrow with day 2 notes. We're going to solve exponential equations, and that'll be super easy. Notes tomorrow will be super short, super duper short. So let's get started, ladies and gentlemen. First thing we need to do is know what we're talking about with a exponential. We should know that we have a base, the big guy, and then the little font is our exponent. So we would say 2 is the base and 3 is our exponent. This means 2 times 2 times 2. You guys know that. We know how to type this in our calculator, right? 2 raised 2. Use this little caret, raised 2. And then the third power, press enter, and we get 8. Okay? Well, now, have you guys heard of growing exponentially? Have you heard that before? Things that grow exponentially. Does anybody know anything that grows exponentially? Use your microphones if you know something that grows exponentially.
Right now, the human population.
The human population, very good. Thanos, right? You guys have all seen Avengers Infinity War, right? The snap, right? Thanos wanted to kill half the population because if we are unchecked, if we keep growing, right, we're going to run out of resources. We're going to have people living on top of people, which we have already in the cities, all right? And eventually we're not going to have enough food or water or what have you to take care of ourselves, all right? There's also, you guys read the Da Vinci Code with Dan Brown? There's also another Da Vinci Code movie that's about that. It's not Angels and Demons, it's the other one. I can't remember what that one is. Has anybody seen the Da Vinci Code movies? It's with Tom Hanks, right? Anyway, it'll come to me. I can't think of it. So fantastic. More population grows exponentially. Can you guys think of anything else that grows exponentially? We're making history right now. What grows exponentially if left unchecked? What's going on? What are we doing right now, guys? We're in the middle of history, believe it or not. Huh?
So, disease.
Yeah, corona, right? The coronavirus. Viruses will spread exponentially unless checked. All right, and that's why we're in these our houses and stuff. Again, you might have conspiracy theories and what have you, but you know that's the pandemic, right? Pandemics are again diseases that grow exponentially unless unchecked. That's why we have this stay 6 feet apart, wear your masks, and yada yada. We're trying to make a curve of this graph. Okay. If you invest your money, you can invest it. Okay. Compound interest, continuous interest will grow exponentially. So as you start getting jobs, you want to start investing your money. Okay. Cancer, cell growth grows exponentially. Okay. So these are all the things that, so you want to know, when would I ever use this? Oh man, right? If you like money, 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 you want to know about exponential growth, right? You want to stay healthy, keep everybody healthy, get out of this pandemic. We need to know about exponential growth. So if I take a look, 2 cubed is 8. If I just change that by 0.1, 3 to the 0.1 power, okay, plug that in. Look at that. It grows up to 8.57. Just 1/10 of a change is almost up to 9, halfway up to 9. Okay. As I grow a little bit bigger, I can do 2 raised to the 3.14 power. That's pi almost, right? Approximation. That's 8.815. And then 2 to the pi, you guys know where pi is, right? Pi is the same button you've been pressing for raised to. So 2 raised to second raised to power. So that is pi unrounded in your calculator, and it even goes up a little bit more. Okay, so your base is staying the same, but that exponent is getting a little bit bigger each time, and it's not going up very much. And look how bigger this number has gotten. Now I know from 8 to 8.85 is not huge, but we haven't hardly changed that exponent. If I change that and I go 2 raised to the 4th, now it's up to 16. And then 2 to the 5th is bigger, 32. If I do, 2 to the 10th, oh my gosh, now we're up to 1,000 already. Okay, so as this number gets bigger and bigger, this thing starts growing faster and faster. It's growing exponentially. That's the idea. Okay, so what we're going to do is we're going to start graphing these things. All right, so I have 3 graphs, and I'm going to plug in these 3 numbers, okay, to help give us a visual of what this graph looks like. So the first thing is I'm going to plug in 1. So 2 to the 1st is 2. So we get the coordinate point 1, comma 2. We got that point right there. I'm going to plug in 0, and 2 to the 0 power, anything raised to the 0 power, is 1. So we get 0, 1 right on the y-axis. And then when I plug in -1, 2 to the -1, we talked about uptown, downtown. If it's uptown and it has a negative exponent, I can shoot it downtown and make it a positive exponent. So I would get 1/2. Okay, so I get -1, 1/2. Okay, so what this graph looks like, and you can plot more and more points, what this graph looks like, it's getting closer and closer to the x-axis, never touches, and then it starts shooting up really fast. If I did 2 to the 3rd, we know that's 8. So 2 cubed would be way up here, and so on and so forth. If I did 2 to the 4th, that would be 16. That'd be off the chart. So I call this a little J curve, okay? And your graph is getting closer and closer, but it will never cross over. There's no way for it to turn into negative. So it's getting closer and closer to 0, but it's never going to touch it. And we call that a line. You guys know what that line is? Where it's getting closer and closer to never's going to touch it. What is that thing called? You guys remember? For large values of x's, it's getting closer and closer to never going to touch it. Sydney, Leo, Ryan, Duncan, Caitlin, you guys remember what that thing's called? Hayden?
Is it an asymptote?
Watch your mouth. Yes, it's an asymptote. So very good. We got a horizontal asymptote at y = 0. Fantastic. Just kidding. When you're graphing these exponentials, you'll have no gaps, breaks, or holes in your graph. There's unlimited x values you can plug in. So we say our domain is from left to right, -infinity to infinity. So it goes all the way to left, and it works its way to the right with no gaps, breaks, or holes. And then our range is bottoms up. You don't see anything until the asymptote. All right, you don't see anything until 0. Now, it never touches 0. But after 0, you see it, and it just goes up and up and up and up all the way to infinity. Okay? And again, make no doubt about it. This number for the range is always referred to with your asymptote, your horizontal asymptote. So the number for your asymptote is always going to be in your range for exponentials. All right? So you could go through and answer and graph these guys. If you want to use your calculator, you could. So if you wanted to graph number 6 on the calculator, to get these points, I go to y = and I just do 4 raised to the x power. So 4 raised to the x And then I'm in Zoom 6, Zoom Standard. And you'll see a J curve that looks very similar to this one, right? But these points are a little bit different. If I go second trace value and plug in some numbers, if I plug in -1, I get 0.25, which is 1/4. If I plug in 0, I get 1 again. And if I get 1, I get my base, which is 4. All right, so -1, 1, 4, 0, 1, and 1, 1, 2, 3, 4. Okay, and then it still has the same things. It's got your asymptote, y equals 0, and then has your domain and range the same. Domain is -infinity to infinity, and your range is the same, 0 to infinity. And then if you wanted to, you could graph the next one. If I plug in -1, that'd be 5 to the -1 power, which is 1/5. 0, you would get 1, and if you plug in 1, you get your base 5. So as you see, the numbers that you get when you plug it in 0, 1, -1, you get very similar numbers, right? And that's where we start seeing the similarities that we have. Okay, at least we should. So I want to talk about the similarities that you see when you have y equals a to the x. When I have y equals a to the x, where a is any real number, it could be 2, 4, 5, whatever. The first thing you guys notice is what? What do they have in common? What do you see with these graphs here? Shout them out. What is some things you see in common? And while you're thinking of that, I'll graph this one while you're thinking. What do you guys see that you have in common here? Or do you not see anything in common? Nothing.
The same domain and range.
Yeah, my domain and range are going to be the same, right? Domain is always all reals, -infinity to infinity, and my range is always from my asymptote to infinity. Which my asymptote, which is another thing they have in common. So my HA for short, horizontal asymptote, is y equals 0. All right, awesome. Look at the coordinate points. What do you notice that they have in common? What will they always have in common? What's the similarities that you guys see? They have a y-intercept of 0, 1. And what happens when you plug in 1? We got 1, 2, we got 1, 4, we got 1, 5. What happens when you plug in 1? What do you see? Zach, Ryan, Lorelai, Caitlin, what do you guys see when you plug in 1? You got a lot of cameras off. Amshel, Jen, what do you guys see? Mare. When I plugged in 1 on this one, I got 2. When I plugged in 1 on this one, I got 4. When I plugged in 1, I got 5. So when I plug in 1, what do you get?
Same number.
Yeah, I get this guy. What's that thing called? That's the exponent, right? And then what's the big number?
It's the base number.
The base. It's all about the base, about the base, about the base. No trouble. Yeah, so we get the base. So if my base is a, then we could say it's 1, a. Okay, that's what I'm looking for. The other thing is when I plug in -1, I get 1/2. I get 1/4. I get 1/5. I get 1 over the base. And guys, those are A's, not 9's. Those are my A's. All right, assuming my base is A. All right, so if I'm graphing these by hand, this is how we graph them by hand. We use these three special points. So if we were doing this without the pandemic and we had to do this in person, we would be using these three special points and using transformations of those. Okay, so these are the similarities you should see. Again, when we look at this graph, they look like that J curve, right? There's an asymptote going across. They look very, very similar. Okay. Now, the nice thing is when we're graphing these, I'm going to show you how to do it using your calculator also. So you should be able to do either method in my math lab. Okay, so but make sure 0, 1, 1 in A, negative 1, 1 over A. When we're learning this in real life, I actually use a little chant to help you memorize these. Okay, and the chant goes 0, 1, 1 A, negative 1, 1 over A. It's fun to say, huh? 0, 1, 1, A, negative 1, 1 over A. 0, 1, 1, A, negative 1, 1 over A. Go lay in some hay. What do you say? Down by the bay. I just might may. Oh, man. All right, so I'm going to write those 3 points. So I'm going to go through, I don't know, 3 examples here, guys. Again, I'm going to also show you with the calculator what that's going to look like. Okay, but I'm going to do it by hand like I would normally. 0, 1, 1A, negative 1, 1 over A. And I always say A is positive. So I always start with A is positive, and if there's a negative in front of it, we'll worry about that later. Okay, so the first thing I look, my base on number 8, I've got y equals 2 to the negative x. I've got A is negative or positive 2, excuse me. So I use my 3 points, 0, 1, 1A, 2. Negative 1, 1 over A, 2. So I got 0, 1, 1, 2, negative 1, 1 over 2. Well, then I see that I have some kind of transformation going on. So I'm going to highlight that for you. Okay, and that little negative is up in the exponents right next to the x, right? So I always ask you if it's up with the exponents. If it's up in the exponents, then it changes the x's. This x has been multiplied by negative 1. This is a multiplier to your x's. So I'm going to take all your x's and multiply by negative 1. So I'm using parentheses for multiplication there. Okay? So I multiply. 0 times anything is 0. So that's point stays the same. 1 times negative 1 is negative 1, comma 2. And negative 1 times negative 1 is positive 1, comma 1/2. Okay? Now I graph those 3 points. I have 0, 1. I have negative 1, 2. And then I have over 1 up 1/2. Okay? My asymptote is still there at y equals 0. That has not changed. But now my graph starts over here and goes up. Okay? Well, if we look at our calculator for y equals 2 to the x, it's supposed to look like this normally. But when you have a negative up in the exponent, it reflects it over the y-axis. So when your x is negative, think of symmetry when we talk about symmetry over the y-axis. Okay, this has been reflected over the y-axis. Okay, so you maybe want to make note of that, is if this is multiplied by the x's, if it's negative, then it's a reflection over that y-axis. Okay. Domain, again, range, same as we had. Domain is all reals, negative infinity to infinity, and your range bottoms up. It starts here at 0 and it goes all the way up. Never touches that asymptote, so it's not inclusive. It's a parenthesis. Always parentheses in this chapter, never brackets. Okay. So I'll show you number 9. We're not going to go through all these. Okay, I got two more examples. Okay, now the nice thing, guys, you could just use your calculator too, right? So if I was going to do number 8 in my calculator, I would just do 2 raised to the negative x power. Okay, and then graph it. And then I would see a nice, pretty graph that looks very similar to the one I just did. All right, and when you're graphing in my math lab, they're going to ask you for probably like 3 points. So you can do second graph as your table and find those 3 points there. Or I prefer second trace value and then type in, okay, if I plug in 0, I get 1. If I plug in 1, I got 0.5. And if I plug in -1, I've got 2. Okay, so you should be able to graph in your calculator and help help graph this. So this is how you do it by hand. This is how you can answer some of those My Math Lab questions. Okay, so you can do either. It's your choice. If this was non-pandemic, you'd have to do this by hand. I'd have to see this work. But it's not, so you don't have to. All right, so let's move on to number 9. Unless you guys have questions, give me a hand. Give me a thumb. Where are we at with this? Are we okay? Because I only see a half of you guys. Give me a thumb. We're good. Okay, let's see this done again. Okay, so I'm going to use my chant. 0, 1, 1a, -1, 1 over a. A is 4, always positive. I know there's a negative there, but start with a positive. We'll take care of that negative here in a second. 0, 1, 1, 4, -1, 1 over 4. But now that transformation I have, that negative, my first question is up in the exponents. Like the x is in the exponents. If it's not, if it's down here, then this is changing the y's. If it's in the exponents, it changes the x's. So this one is down with the y's. This is a multiplier to your y's. In fact, if I wanted to, I could divide it over. It would be -1 times y. Okay, so I'm going to take all my y's and multiply by a -1. Now this is pretty easy to do. Just putting little negatives up there. So now instead of 0, 1, I have 0, -1. I have 1, -4, and I have -1, -1/4. So this thing has been flipped down here. This one at 1/4 is now at 1, -4. And then -1, -1/4. Your asymptote is still at y equals 0. But now it starts here, and it works its way away from the asymptote. It goes down. It's going down. It's yelling timber. You better move. You better dance. So what happens with this one, it's a flip. Normally, it's here, and now it gets flipped over. Okay? So if you want to make note of this, this is a reflection over the x-axis when you have a negative. So that's a reflection over the x-axis when the y is negative. Now, domain does get switched around a little bit. Okay, when you get this thing flipped, then your range gets flipped. So how low does it go? This thing goes all the way to the flow. This goes all the way down to -infinity. How high does it go? Does it go up high all the way to the sky? No way. It stops right here at 0. So you can see the difference between these two. This one starts in 0, goes infinity. When it gets flipped, your range gets flipped, starts at -infinity, goes to 0. Okay. Do we have any questions there? All right. Now, again, nice thing is if you want to throw this in your calculator, you could. Right? If I want to do -4 raised to the x power, graph it, you get the same graph. And you want to find points that way, you could do it that way. This is how you do it by hand using transformations. Okay. All right. Let's do one more. Just do an 11 before we get out of here, and then I'll make an embarrassment on myself and my kids. So do reflections first when you're looking at 11. If I look at 11, the first thing I see is I have a base that's positive 2. Okay, so I see I've got 0, 1, 1a, negative 1, 1 over a, 0, 1, 1, 2, negative 1, 1 over 2. Well, now I have two things going on here. I have this negative, and I have this plus 3. Now think back of quadratics. If I had y equals x squared plus 3, that would be a shift of my parabola up 3 units, right? And if I'm going up 3 units, that's addition to my y's. And we talked about in the last example, this is multiplication to the y's. All right, do you see the difference? So this is multiplication, this is addition. Well, which one do you do first? Well, we always use, please excuse my dear Aunt Sally for doing this by hand, where we do multiplication first. Okay, we do the reflection first. So take your y's, this is a multiplier to the y's, and take all your y's and put a little negative in front. And that way we have that negative 2. Everybody does this negative 2 in this one, but they forget the 1. So that's why I always say the base is 2, and then do the multiplication. Okay? If you're doing this by hand. Now this thing is getting shifted up 3. Okay, what does that mean? Well, normally my asymptote is here. It's now going up 1, 2, 3 units. So this is actually your location. 1, 2, 3. This is the location of that horizontal asymptote. So I'm going to take all these y values now and add 3 to them. Add 3. So my final coordinate points by hand would be 3 minus 1 is 2. So 0, 2. Negative 2 plus 3 is 1. So 1, 1. And 3 minus a half is 2.5, 2.5, whatever you want. So I graph it. Remember, it's a reflection down. It's going to look like this one up here. And it's been shifted up 3 units. So I've got 0, 2. It's right there. I got 1, 1. And I got negative 1 and 2.5 right there. It's not a straight line. It starts at the asymptote, and it's a J curve away from the asymptote. Looks like a J. In this case, it's been upside down. It's been flipped, and it's been shifted up. Again, your domain is always the same. All reals, fancy R, negative infinity to infinity, whatever you want to write. And my range goes all the way down to negative infinity and works its all the way up to the asymptote of 3. That's how you do it by hand, ladies and gentlemen. All right. Questions on what I'm doing? Now, again, nice thing is a lot of us have these calculators we can use. I got negative 2 raised to the x, get out of there, plus 3. And if I'm trying to graph this using my math lab, I need 3 points. Just make sure you type it in right. And now I can go second trace value and type these in. I can type in 0 and see what I get. I can type in 1. I get 1. I can type in negative 1. I get 2.5. So you guys have other options instead of doing it by hand. Okay. Any questions, y'all? Any questions? Last but not least, so I'm skipping over 10, 12, and 13. We don't need those. Okay. Especially if you can use your calculator. Last thing we're going to do is, what is the number E? All right. We know what pi is. We know pi is 3.14, right? Well, we're looking for the number E. All right. And to help you out, I've got a little song to sing. You can sing it with me. Do you guys remember Lion King? You can turn your mics on and be part of this. Oh man, I'm excited. There's a number, a special number, we use it constantly. There's a number, a special number, we use it constantly. You've heard this one? E 2.718. E 2.718. For logarithms, yes, logarithms, the base is naturally E. Oh my gosh. For logarithms, yes, logarithms, the base is naturally E. What's E? E 2.718. Look at this. E 2.718. And now this is the dancing. You can dance. Da 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 dee da dee da. I can get my whole body and do a little dance here. And then you spin around. And then we dance. Spin. Oh, to compound interest, continual interest, it's pert shampoo for me. To compound interest, continual interest, it's pert shampoo for me. E 2.718. E 2.718. All right, ladies and gentlemen, I just made people leave. Look at that. They had to shut that off. Ladies and gentlemen, we're talking about the number E is 2.718. It's an approximation. It's a number that we use a ton for compound interest and continuous interest. Okay. This PERT shampoo is our continuous interest formula where we have A equals principal times the number E. E is a number raised to the RT power, rate times time. Okay. For logarithms, yes, logarithms, the base is naturally E. When we're talking about logs of naturals that are natural, those bases are E. And again, E is a very special number, and it's in your calculator if you ever forget that beautiful song I just sung you. All right. If you look at your raised to, you guys know where pi is, right? Pi is right there. Go right underneath of it, division. Second division is E. So if I go second division, I get E. Okay, 2.718. Okay, again, 2.718 is its approximation, like pi is the approximation of 3.14. You could also do second e to a power, which is natural log. Do you see log? Under that is ln. That's the natural log. Okay, so if you do second natural log, you get e. All right. So when you look at these graphs, if you ever need e, you just use your points. 0, 1, 1a, negative 1, 1 over a. And then we could graph this thing. 0, 1 is right there. Over 1, up almost to 3, and then down here really close to that asymptote. Okay, it gives you a rough sketch of what that graph would look like. All right, ladies and gentlemen, hopefully you did not chat snap that to anybody. You guys have homework tonight, 5.3, day 1. You guys have a great day. Let me know if you have questions. Stick around. I can go over a few things for you.